Good morning, everyone. Welcome to the 5th Dry Scrubber Users webinar. This one is going to be about dry scrubbing consumables. I'm your president of the Dry Scrubber Users Association, Jerry Hunt. For those of you that have been here before, you've probably heard this spiel multiple times, but for those of you for the first time and not familiar with DSUA, we're a nonprofit organization that was developed in 2008, and the goal and the objective was to foster and collaborate both innovation and develop a network for folks in the dry scrubbing industry, various technologies, circulating dry scrubbers, spray dryers, dry sorbent injection. So again, this is our 5th webinar of 2020. Webinars were something that we constructed since we didn't have a conference this year due to COVID. And this will be our final webinar of the year, but the intention is going forward in 2021. We're going to continue doing these monthly webinars with, again, continuing dry scrubber content. So you guys like what you hear, and please come check us out again in 2021. If you're interested to talk and present during one of the webinars, then please reach out to us through the website and submit an abstract for consideration. As for today's webinars, again, these are consumables. So as we kind of define these, any aspect of the dry scrubbing technology that gets used up or replaced. So whether we're talking about filter bags or hydrated lime, quick lime, any kind of spray nozzles, etc. So those are anything that falls under the umbrella of consumables. So that's really the target of what we're going to be talking about today. So we have presentations from Andy Paul and Maggie Skelton of Boswell Energy talking about the Unit 4 NID system they have at their facility. And we've got Shawn from RPM and Claude from Omaha Public Power District. Public Power District. They're going to be talking about OPPD as well as the spray nozzles. So if you guys have any questions in the platform, submit them through the Slido. You'll see that below the viewing window. If you think of them afterwards or have issues submitting the questions in Slido, feel free to email them to DSUA through our website. And if we don't get to your questions today, we'll do our best to kind of follow up and make sure all the questions get answered. So again, this webinar is going to be recorded. So whether you hear something you like, you want to go back and view it again, you want to share this content with someone that couldn't make it, or you simply just got to hop off early, stay tuned. Once this is uploaded to YouTube, we'll distribute it out there, and it'll be on a public forum. So feel free to distribute and watch again as you guys see fit. Also, take note in the platform that there's going to be polls that are going to be cycling through the platform. So feel free to submit your responses to those. That's important feedback to DSUA. First and foremost, I'm going to pull up some slides. We want to thank some sponsors here. Oh, there we go. I want to thank some of our sponsors for the webinars this year. That's been very important for DSUA for, the sponsorship. It kind of, again, being a nonprofit, a big part of it this year of being sustainable and continuing for 2021 has been the support we've got from not only people joining and participating, but our sponsors. So we want to acknowledge and thank them. Our first sponsor is Lhoist North America. They're a subsidiary of the Lhoist Group. They're a global limestone, quick lime, hydrated lime, silicate minerals company. They supply multiple high-quality calcium products, including their enhanced hydrated lime products, the Sorbical SP and SPS, designed with higher surface area, higher porosity. And these are utilized for a multitude of acid gas solutions at whether it's DSI or circulating dry scrubbers at power plants, as well as a multitude of industrial applications. In addition to their products, Lhoist has a team of flue gas treatment experts that have several decades of air pollution control experience. So they're there for additional support for custom solutions, whether it's in terms of compliance, optimization, some troubleshooting, anything in regards to your dry scrubbing application, reach out to them. One of our other sponsors this year has been Reaction Analytics Solutions. They specialize in providing engineered solutions through their CFD modeling designs and expertise. The founder, Dr. Guisu Liu, he's got over 20 years of working experience on CFD models, as well as fuel combustion and emission control technologies. And as a result of his experience, he's developed over 100 CFD-based model engineering solutions. So whether you've got a need for some front-end combustion or you're looking for something on the back end for emission controls, Reaction Analytic Solutions has got the CFD experience to try and help you through your needs. So their unique CFD solution includes chemistry modeling as well. So it can help you optimize both chemical as well as sorbent usage. So this one great example is Reaction Analytic Solution has been used for fine tuning DSI performance, optimizing sorbent distribution, kind of saving you some field work through these CFD modeling programs. So if you're looking for CFD modeling, come check them out. They're some of the best in the industry. Primex is probably a name for those of you in DSUA. They've been involved from the start. They provide comprehensive programs to help dry scrubbing users optimize their performance. They've got a unique combination of the dry scrubbing knowledge, technology, as well as just overall patience that's evident in their track record of their 20 plus years of customer successes. So you can see some of their customers here, some familiar names. And if anyone tuned in on the last Dry Scrubbers users webinar with Dryforks, you get kind of a sense of what they bring to support their customers. So having said that, again, thank you to those sponsors. We couldn't do it without you guys. Now I want to kick over to the real meat and potatoes of why we're here today and start with our first presentation. First presentation again is going to be Andy Paul and Maggie Skelton from Boswell Energy to talk about the Unit 4 NID system consumables. And just wanted to kind of introduce Andy and Maggie. Andy is a technical coordinator of operations for Boswell. He's been with Minnesota Power for 11 years and worked across all 4 of the units at Boswell for the past 7 years. Previously, he's also worked in their environmental compliance department. So it sounds like, multitude of operations and environmental compliance. So, he'll be here to answer any of your questions as well. Maggie's a senior engineer for the generation reliability. She's been at Minnesota Power for 14 years in a variety of roles throughout the engineering department. She was a core member of the NID engineering, design, procurement, and installation team from 2012 to 2015. So having said that, Andy, I'm going to turn it over to you and feel free to put your slides up. And thank you. Thank you for the presentation.
All right, I gave everybody a quick preview there because I was at the last slide. Hi, everybody. Andy Paul, Minnesota Power. I'm at the Boswell Energy Center, which is in Cohasset, Minnesota. And we're talking about our NID system, which is a circulating dry scrubber. It's this building with the star on it. I'll just go through a quick outline. So obviously I'll give you an introduction of who we are. I'll do a quick overview of the NID just so that everybody understands the general concepts and layout. We'll talk about a couple of the improvements that we did. A big one for us was the fabric filter improvements. And then I'll slide into talking about reagent optimization. We've done quite a bit of work with our line conveyors and then our ash reusage. And then lastly, we'll talk about water usage and things we've done to really maximize our reuse of source water on site. So who we are, Minnesota Power, we're a subsidiary of Elite. Minnesota Power is the owner operator of Boswell Energy Center. Boswell's been in service since 1958. We recently decommissioned the 2 original stations. They were 75 megawatts stations. Unit 3 is in service. It's a 350 megawatt unit, and that's been in service since 1973. And Boswell 4 is a 585 megawatt unit, and that's been in service since 1980. In 2009, we completed a back-end retrofit on Unit 3 to upgrade our pollution control equipment. And in 2015, we completed a similar back-end retrofit on Unit 4 to upgrade our pollution control equipment. Who am I? I've been in the operations group here at Boswell, specifically kind of plant, working directly in operations for 7 years, and before that, working at the plant site in environmental compliance. So fairly well versed in the regulations that we have to comply with, and also the various operational systems we have at the plant. And then Maggie is my counterpart. She's going to help me out if we have any questions. Obviously, she's a senior engineer, and she has played a large role in the NID design and installation. And then also, she works on a lot of the water balance stuff here at the facility. So she's pretty knowledgeable about our water usage within the NID process. Just a couple more introductory things. We're located in northern Minnesota. So we feel that gives us some unique operating parameters. For those of you that are familiar with Minnesota, we're basically right between Bemidji and Duluth. And this is kind of my icebreaker. I'll put that in quotes because we do take a point of pride in being able to manage and operate our facility through some temperature extremes, and we really try to optimize our cold weather operation. That's a peak load time for us is winter time, and we do have several large industrial customers that take a lot of load in the winter. So where we're at is in Minnesota. Just a few examples. Our record cold temperature is 60 below. February is a really cold month around here, and then we can have wild temperature swings in February. You could go from 50 below to 20 above. We get snowfall 9, 10 months out of the year. We really don't like it when we get snowfall at that time, but we do have measurable events throughout the year. And then we can have large storms. Everybody can have large snowstorms, but we just kind of deal with the full gamut. And again, a little bit of a point of pride with dealing with some of the weather misery is that these are the records, but we do come close to breaking one or more of these every year. So it's a consistent piece for us to optimize for cold weather operation. Sorry about that, skipping around. This is just the plant footprint at Boswell. So we've converted Unit 4 over to the NID system, and we're working through a pond dewatering process. So we are using a lot of our pond water, trying to integrate that into our NID process as best we can. Other things I want to point out is we're located right off the Mississippi. That's our source of service water for the majority of our service water needs. A little bit about the NID. It's a, like I said, it's a circulating dry scrubber. It's an Alstom design. Our facility, since we are so closely butted up against the Mississippi and its backwaters, we had to really design the NID to fit into the footprint we had available, so that we wouldn't trigger any wetland impacts or other things of that nature. So with that, we have kind of a vertical design. It's a 9-module system with one redundant module, so we can maintain full load with 8 modules in service and take one out for maintenance. We stack that up kind of A to I down the line, south to north. Each module has 2,160 bags, so that's a total of 19,440. And then we use quicklime material, fly ash, sort of recycle to as our removal media for SO2, SO3. And like I said before, this is specifically designed to fit into this footprint. We had a lot of lessons from our Unit 3 retrofit as well on technology and what we could do to minimize costs. without having to put a lot of steel framework in place. So I'll just give a general overview. This is our control screen, but it does help to show kind of the internal layout of the modules. So we do have inlet flue gas coming in, and then it runs its course through the modules. We do the reagent injection, and then collect it in the fabric filter, and then it goes out through the outlet duct. Some of the important technology of the NID is this J-duct design. It helps to get the appropriate flue gas distribution and speed, so that when we do inject the control media, we're having enough resonance time and enough distribution to get the proper neutralization effects that we want to see. A couple of the main components here is the hydrator. So our lime is conveyed to the hydrator, and then we also have the recycled rotary feeder, which is taking the recycled ash component. We put that into the mixer, and that meters and injects into the ductwork based upon airflows and whatnot. Any heavies that we do have that fall out of the flue gas entrainment pathway, they do come out the bottom of the J duct, and we convey them out and have a removal process for those heavy materials. A little bit more about the NID. So this is kind of helps give you the picture of the ash recycling. So we have the flue gas that's coming in. It's going through the fabric filter materials, which are located here. We have it's a pulse jet system. So as we remove ash, it falls into the fluidizing trough. And from the fluidizing trough, we remove a small portion, send that out to our ash silo. That just helps us to be able to inject new material. And then the majority of it is recycled through the process, and that goes to that rotary ash feeder that I pointed to on the last page. So this is a kind of a key component for us to minimize reagent usage is being able to optimize our amount of recycled ash we can use. And just one last NID kind of layout overview here. So again, we're injecting our media from the mixer essentially, and using the J duct to reach the appropriate flue gas flows and distribution, where it then heads up to the bag house and then out through the outlet duct. A couple of key components here: our lime feeder and our lime conveyor that feeds the hydrator, and then as well the hydrator then feeds the mixer, where it combines with the fluidized recycled ash. So a key component for us, we've done a lot of work with over 19,000 bags. We do have they're a key component of the NID, and we've done quite a bit of work to reduce the frequency of broken bags. When we do have broken bags, it affects our opacity and PM, and oftentimes we have to take modules out of service to be able to maintain compliance with our air permit, and also to fix the associated problems. So a couple things that we've done is we've worked with sleeve insert, and we've also done a cuff redesign. The picture I have here just shows the blow tube, which comes off the pulse air header, and then this is just the bags within the cage. So this does not show the sleeve inserts, but it gives you a general concept of what we're looking at here. So what we've experienced is a high volume of, we would say, relatively high volume of bag failures. So in 5 years of operation, we've had 3 to 4% of our bags that have had failures, and where we've seen the vast majority of those failures is at the the cuff where it comes in contact with the snap ring. The snap ring is part of the bag cage. We get a lot of wear between the snap ring and the cuff when we're pulsing those bags. So we've done a couple different things over the past 5 years to kind of combat that. You have two sort of sources of wear. One is just the pulsing itself. The other is over time, those blow tubes. They can, as they heat up and expand, we can have just slight misalignment, especially in our first two rows. And we've seen a lot of wear in our first two rows of bags just because of that slight misalignment. So you get kind of a double compounding effect there of wear. So some things we've done to combat that. This is a sketch, but we've created a sleeve, and we use this mainly in those first two rows. It's about a 4-inch total length, and it inserts right into the bag. And what it does is help to minimize the movement between the bag and the snap ring. We've seen that it does not affect our bag performance or cause degradation. And we were able to make them out of mild steel. We didn't have to use any special type of stainless, and we made sure that they were heavy enough that they did not get moved around when the pulsing went off. This has been a very valuable tool for us. It's helped us to eliminate or slow down the degradation, especially within those first two rows.
Hey, Andy, this is
yes,
real quick. What you mentioned that the blow tube misalignment primarily in the first two rows. Do you guys know what in particular about the first two rows seems to be the cause that it seems to be more problematic there versus throughout the baghouse?
I'll move up to a slide here.
Jumped ahead.
This is the blow tube itself, and we don't have besides some re-engineering of the tube sheet. We've tried to make adjustments to these blow tubes, and for whatever reason, as we get extended run times, especially full load hot weather, we will get some expansion, and we believe we're even getting more pressure coming out of those first two rows. We don't have a super good answer. We are changing all our bags out here, and we're going to be replacing some of these blow tubes that have been in there and have given us historical problems. I know our engineering staff is kind of looking at this diligently, trying to figure out what other steps we can take to prevent that misalignment.
Okay. Hey, we do have one question also from Slido that came in. If you're ready to take it. The question is, what is your fabric filter differential pressure cleaning set point, and what pulse pressure are you using?
Let me look here. I'm going to back up a little bit. So this probably helps. So our pulse pressure is generally 55 pounds. We've tried higher or lower, and we've seen really no difference in result. And we generally maintain a DP. It's slowly increasing. We have about 5 years of life on our bags here, but we're typically in the 7 to 9 range.
Was that, I saw there was a pressure on there for your pulse pressure. Is that on the top? Oh, is that at 55? Is that
Yep.
what?
Yep, that'd be our pulse pressure. Yep.
Gotcha. Okay, thank you.
So as I mentioned, we had due to the pandemic, we had to push off a long outage we had scheduled this spring. So we have gotten some extended life out of our bags that we didn't necessarily plan for. but one item that it gave us time to do was we've come up with a cuff redesign to help combat some of these problems we're seeing at the snap ring. So two of the things that we're doing is we've added a wear resistant material. So that's the gray material in the picture. It's kind of like a sort of a Kevlar type material. And that's to help protect against wear from the snap band itself. And then in addition to that, we've actually made the cuff thicker so that we have a tighter fit and hopefully have reduced movement and wear associated with that. So this we're hoping will be a big change for us and help to improve the issues we're seeing. I guess one thing I'd like to add as well is, we're in our first 5 years of operation within the NID. We obviously probably had some growing pains in the first year or two, and some of the things that we've seen are just those growing pains coming to fruition. We've had a number of other optimization efforts and improvements along the way. So we really expect to get some long bag life going forward.
And how long ago did you make these cuff redesign modifications?
So these will be going in place this spring. We intended to put them in spring of 2020. They'll be going in the spring of 2021. We had to push off our long outage due to COVID. But it gave us time to refine this process, and we've even done a few test bags, and we feel like it's going to be a really good fit for us.
Excellent. Okay, thank you.
So now kind of moving into reagent reduction efforts. We've done a few things. One, strictly to minimize lime usage, and then the other is to optimize how we use the recycled ash, which in turn helps us to reduce some lime consumption. A big thing for us was the lime feed zero speed adjustments. So like most coal-fired power plants, we're living the new life of cycling load, and when we have low loads, we often could not inject lime low enough without tripping out our lime feeders. So we had additional usage that we didn't need for SO2 control simply because we couldn't get the feeders to run down low enough. What we did to try to combat that is there's a drive package for low RPM operation. It's called a flux vector control. Now, I'm an operations guy. I'm not an electrician guy, so I'll do my best. But we installed this flux vector control, and essentially it allowed us to run the drives down to a very low speed and prevent them from stalling out when we had very low hertz on the drive. And this has allowed us to, we have a minute and a half delay before the feeder trips. When we have excessive feeder trips, operators wind up just biasing up the feed rate so that they don't have to continuously reset the feeder, and therefore we go through more lime than we need to. So we were able to, we originally the speed sensor trip was 30 seconds. We've been able to increase it to a minute and a half through trial and error. And then the installation of this lower RPM operating mode has really helped us to minimize our usage when we're down at low loads, which, for example, this past year for us, April, May, June, September, and parts of October, we see fairly frequent low load operation due to high wind. So it has been very helpful from reagent reduction standpoint. The other piece here, I'll just kind of lay out. So Unit 3 and Unit 4, we collect their ash. Unit 3 has very sellable ash, and we have an ash vendor that we work with on a consistent basis. and we don't have to landfill any of the Unit 3 ash, which is nice. Unit 4 ash, because of the lime, it's not beneficial for the marketplaces that we have available to us. So we wind up landfilling Unit 4 ash. So we've done a couple things to try to maximize our reuse of that ash before sending it out to the silos and ultimately landfilling it. A couple things that we are able to do is whenever we have to empty out our troughs, we have to change a fluidizing cloth in the bottom of the trough or whatnot. We're able to work with the ash vendor and they can unload from the Unit 4 silo and load that ash back into our troughs. So we're able to reuse our own ash and not have to go out for hydrated lime in the events that we have to empty out our troughs. Another thing that we've worked to do to allow us to empty out the Unit 4 silo on longer outages and whatnot is we've done a lot of trial and error and testing to verify that we can keep that ash in our troughs. So what we've done here is really used moisture content. And originally we had a 7 to 14 day window, and we've been able to expand that out to 28 days that we can maintain that ash in that trough and not have to empty it out and not have to refill it. So there's definitely a cost savings for us in not having to buy hydrated lime, not having to pay ash vendor to help us load ash into here, and also gives us the opportunity to do maintenance on our silo when we have time during longer outages. So it's been a pretty good effort for us. If we leave this ash in here too long, just for everybody's understanding, if we leave this in here too long, we're going to get a lot of solid and heavies, and we're going to overwhelm our grit conveyor down below, and that causes a lot of operational headaches trying to remove that material from the J-duct efficiently. So it's a fine line to walk, but we think we found a pretty good cutoff at that 28-day mark. And obviously there's a little seasonality to that, but we've tested that across the board, and that's where we came up with 28 days. We probably could get 30 at certain times of the year, and but it's just it's a easy number for us to remember, and fits nicely with most of our outage lengths.
And how frequently is this? Primarily during outage, or how often are you guys having to kind of use that Unit 3 ash over in the troughs on Unit 4, typically in a year?
Well, so it'd be Unit 4 ash, and typically in a year, we'll have to clean out a trough. It depends. We've had more instances when we had higher bag failure rates, because sometimes we'd have to drop the bag down into the trough, and in order to retrieve it, you have to either fully empty or half empty the fluidizing trough. So that's part of the reason we came up with this, hey, let's pull it out of our silo and put it in there. We were experiencing a lot of times where we'd have to refill the trough. Normal operation where you don't have a high bag failure rate, we probably have to refill a trough maybe once a year, and that's typically during our longer outage of the year. All right, next I'd just like to talk about our process water optimization. And this might not seem like a consumable to a lot of folks, but for us, it's the back end of, we have to treat this water if we can't find a place to reuse it. So there is a definite cost savings for us when using as much of our industrial and process waters as we can versus service water. So we do have 5 streams we can use in the NID. We can use service water, which we get from the river. We can use bottom ash return water. The previous Unit 4 pollution control system was a wet scrubber system. We can use water from that wet scrubber pond. And then on Unit 3, we have a wet FGD, so we can use water from that FGD source. And also we can take advantage of our cooling tower blowdown and use that as part of our process water as well. So all these streams combined help us to optimize our strategy for meeting coal combustion residual compliance as part of our company strategy as we work to dewater our pond structure. And it's a cost savings to us and our customers to be able to reuse this material. So a couple things that we did in order to be able to optimize the materials we can use, especially when it comes to things like cooling tower blowdown and warmer month operation. We have these self-cleaning strainers, and this has been a big piece for us. We're able to use water that has higher suspended solids, and we're able to filtrate it. And then as part of that, we take the backwash water from this and we put it in our Unit 3 limestone slurry tank that feeds the Unit 3 FGD. So we're kind of able to reuse all of that water internally without having to add additional surface water to the system. Where we do see the impacts of using the different water sources is mainly at our sprays, our hydrator mixer spray nozzles. What we have done to combat that is we take and we do close monitoring of our mixer amps, and what that tells us is the higher the mixer amps go means that we're not getting necessarily consistent hydration throughout the mixer, and that tells us that we're either having an issue with spray direction or spray volume. So by monitoring mixer amps, we're able to stay ahead of certain issues. And then in addition to that, we've modified our cleaning cycle and our cleaning process to be able to clean all the nozzles frequently. And I think we're able to interject that into our operational processes without interruption. And the way we're able to do that is we just juggled around some of our responsibilities and sort of switch things around so we could dedicate a little bit more time to nozzle cleaning, and that allows us to use these alternative water sources. With that, I guess that kind of brings me to the end of the presentation part. I'm open to answer any questions, and this is just one of our many friends out at the facility. They love the coal pile for some reason. It must be warm on their feet or something like that, but they love to climb around out there.
Thanks, Andy. We did have a question coming from on the Slido. The question is, have you noticed a correlation between modules with filter bag failures and which modules you cycle for load changes?
We haven't necessarily saw that as our issue. We do try to work pretty diligently to alternate the modules that are coming out of service. What we have saw is we've had more bag failures in the first modules in the layout than in the last modules in the layout, and I'm not sure if that's because we're able to more easily detect them if they see more loading, or it could just be a factor of temperature differences from module to module as well. We haven't specifically though had like, yep, it's definitely, we see these three modules. We've had the problems throughout.
And as you guys mentioned, you know, how you guys are having a cycle load and you have 9 modules. What's your normal day to day as far as how many modules are operating? And from your operating philosophy, do you guys tend to operate the same few modules or cycle through them, or what's your philosophy there as well?
So we as we ramp through loads, we typically will go down all the way down to 4 modules in service, and then as we come up on load, we'll add modules in. So we run I would say we run in the ranges of 4 or 5 modules, and then on the top end 7 or 8 modules. And we alternate kind of our, I'll call them sacrificial compartments, but we alternate our set modules. So on a monthly basis, we'll go from, it's these 4 modules, other set modules, and we'll alternate that so that we're not always beating up the same compartments. And then as we take modules out, our control room operators are very diligent to try to not always take the same module out of service at the same load range. And a lot of times what we've run into is maintenance also plays a factor in how we operate it. So if we're doing specific maintenance on one of the modules, whether it be in the fabric filter area or elsewhere, that changes our strategy a little bit, but we always try to cycle through and do the same maintenance routine for the same duration, as we go through all the modules. So we try to do our best to not load up one module with more operating hours or more ash loading than the others.
Got it.
Hey, Andy, you mentioned that this is Travis. You mentioned that in order to use these different water sources, you had to modify your cleaning practices for the mixer hydrator lances. I'm assuming that means you're cleaning them more frequently. What frequency are you cleaning those at? And are you doing something different as far as cleaning, or did you find something that you could use to clean them with to dip them in that may make it quicker or easier? How did you change things?
So we've tried an abundance of things. One thing we did is we added a few more nozzles into our rotation so that we can change them out, and then if the operator can't clean them right then and there, they can go do a task, come back and do cleaning. We have done some chemical cleaning. What seems to work best for our process is actually manually cleaning, and part of what we've done is just give ourselves the additional nozzles so that we can swap them out and maintain other tasks, and then come back and do cleaning as needed. We've gone through a variety of tools, and really we've come up with some pipe cleaner that we operate off a drill, and that really seems to do the ticket to clean it up well. And then the other factor is we do use our maintenance group to help us go through and pay attention to any issues that we might have on the nozzles themselves, clean off any burrs. If we need to realign the angle on the spray deflector or things like that, we try to use our maintenance group to help us out with that on a periodic basis. And that's essentially what we've done. As far as how often we clean, we try to clean all the nozzles twice per shift, and again, the way we've been able to help manage that is to have additional sets of spares so that we can work our way through it, but not have to be solely focused on that for hours on end.
And how long is it taking you guys to swap out nozzles? What's that duration typically?
Per module, it probably takes maybe 10 minutes.
Okay. And as far as the all those different water sources, what are you guys seeing or just to be aware of from a water quality perspective that from these different sources that are being, I'll call it bad actors that are causing or can cause nozzle related issues or operational issues? What are you guys seeing to be aware of?
To be honest, the source that we have that gives us the most trouble is cooling tower blowdown, and the reason that gives us the most trouble is because it has the highest amount of suspended solids, and we backwash those strainers very continuously, and then we have a harder time managing that addition to our lime slurry tank for the Unit 3 operation. We've worked really hard to make sure that we're trying to keep a balance. We aren't able to optimize or fully use all of the Unit 4 water at the same time. We do lean pretty heavily on either pond 3 water or bottom ash water. They just have we have less pluggage problems with those two. So we kind of have a set amount of unit 4 water that we'll use, and then we fill the rest of the process water demand with pond 3 water and bottom ash return, just because they're a little cleaner.
Okay. We do have a question that came in through Slido, and the question is, have you tried changing the sequencer to skip the first couple of rows in the baghouse on the cleaning cycle?
That's a good question. However, I think I may not have described that. So it's basically the first 1 to 2 bags per blow tube. So it's not the blow tube row. It's the first blow tube nozzles on each blow tube. And I can't remember off the top of my head how many blow tubes there are per module, but we can't really adjust that sequence. What we have tried to do, like I said, was we really played around a lot with pulse pressure, and what we found there is we didn't really buy ourselves any more or less bag failures, and we really didn't have even a great effect on DP. So we kind of just went back to our original set points on that.
Okay. Let's see. One question that I had too, just thinking in generalities, as it stands today, you guys have made some modifications, but what is it today that's still, I guess, causing you the biggest amount of heartburn, working with the NID solution right now? Like what do you guys aim to want to fix that's the biggest issue at the moment?
Our biggest, I would say, at least from an operational standpoint, our biggest problem is mixer pluggage. And part of the factor there is not so much the water quality we use. It's that we have we're not optimized to have the best temperature coming into the NID, and we have a little bit of a issue with flue gas temperatures, and that kind of affects our reaction and whatnot. So a big change that we're going to be doing there is we're actually, as part of our CCR compliance, we're adding a thermal evaporator, and that evaporator is going to take a slipstream of flue gas. We'll use it to evaporate water, and then we'll add it back into the flue gas stream, and that'll help knock down some of that temperature, and we think that's going to help us with limestone injection reduction. It's going to help us with some of our mixer pluggage, because we'll be able to better balance hydration, water, and limestone, and reuse ash within the mixer. And we're going to probably see just slightly better reaction occurring in the ductwork, in the J duct work before the fabric filter. So that thermal evaporator is we suspect is going to be a very beneficial addition to our process. And where some of our flue gas temperature issues come from is air heater changes that have been made over time, versus maybe engineering changes that we had, or engineering design. So we have just a higher operating flue gas than is optimal for the NID itself.
Okay. You got time? One last question. One question I had is, when you were talking about the all the bag cuff issues, is there something unique about, your design or your plant that's causing that issue, or is it something that you've seen or heard maybe other folks that have NID systems as well? Is this been a common problem, or is it unique to Boswell?
Um, from my understanding, I haven't been heavily involved in the engineering of the fabric filter, but we do run. We do have 2 fabric filters here at Boswell. Our Unit 3 system is different, and I think what we're seeing is this is part of the pulse. My understanding is the pulse system, the pulse cleaning system, can create additional bag movement than what we the pulse system we have on Unit 4 is maybe a cause of the additional bag movement, and part of that is a little bit of the misalignment issue, and part of that is that I think we had, I wouldn't say we had bad bags, but we had some initial failures when we first ran the NID, and we didn't necessarily have changes put in place, and we're probably seeing, the fruition of those operational issues come to light here.
Okay. Well, we're out of time. Andy, I want to say thank you. Some good stuff here. And once you guys get a chance to install those bags, those new bags in your spring outage, it would be interesting to, hear how the results have changed or what you're observing. So, yeah, so thank you for that. I appreciate you and Maggie both for participating and presenting today. Before we turn over to our second presentation, I just want to make everyone aware that's on the Slido, looking at the polls, that there's a new poll question up. So we'll leave that up for a little bit into this next presentation. So if you get a moment, appreciate your commentary on that poll. And one more thing wanted to do, I'm going to share my screen here. So again, want to thank and acknowledge some additional sponsors here for dry scrubber users for this webinar. So hopefully you guys are seeing my screen right now. And again, want to thank Gecko Robotics for their sponsorship for this webinar. Gecko uses revolutionary wall climbing robotic technology for inspection of various infrastructure. So whether it's a silo or the internal of a scrubber vessel, their robots and their inspection team are been using this technology to perform these NDT inspections all across the globe. Excuse me. End users have the ability with this technology to perform these routine inspections in hazardous environments, and able to do them quickly and most importantly safely. But at the same time, they're also able to generate a amount of inspection data that they can be used for getting the most out of these inspections. So again, thank you for Gecko's support. Mississippi Lime is also another one of DSUA's webinar sponsors. They've got over 100 years of world-class production of calcium-based products. So quicklime, hydrated lime, limestone, from one of the richest limestone reserves in the world out of Missouri. They've got over 12 plants and terminals to provide supply of their products throughout North America that are used through a multitude of dry scrubbing technologies. Again, please, you will learn more. You're using lime, hydrated lime. Reach out to Mississippi Lime. You can get to their website through the Dry Scrubber Users website. And lastly, I want to thank National Filter Media as well. NFM was founded in 1906, which makes them one of the world's oldest providers of air pollution control filtration products. While the industry has changed a lot since NFM came on board, they still have a focus of the same fundamental principles from day one, that they want to earn end users' trust and develop long-term partnerships with products and customer service. So you've heard a lot about filter bags in Andy's discussion. So these might be some appropriate folks to reach out to if interested in further conversation. And again, overall, some additional sponsors want to acknowledge the Carton Fujikin as well, Graymont, and RPM Solutions. You're going to hear from their president, Shawn, here shortly, as well as US Lime. So If you hear anything from any one of these sponsors and you'd like to learn more, please visit the Dry Scrubber Users website. And if you yourself are interested in sponsorship for the webinars in 2021, you can also contact us through the website. So having said that, we're going to kick over to our second presentation of the day. And I want to introduce both Shawn from RPM Solutions as well as Claude. Shawn is the president of RPM Solutions as well as a co-founder. In RPM, they've been a manufacturer of dry FGD components such as nozzles. Shawn is a native of South Dakota, and he's got his mechanical engineering degree from the South Dakota School of Mines and Technology. You guys, if you've been involved in dry scrubber users, you've probably come across Shawn's name or in person. He's served multiple terms as the DSUA treasurer. He's also our current treasurer and the treasurer going forward. And he's also served a term as a DSUA president. Similarly with Claude, if you guys have been involved in DSUA, you've probably heard multiple presentations from him over the years. You can find him in our archives. Claude is the lead system engineer at OPPD, and both Shawn and Claude will be giving this follow-up presentation. So Shawn, go ahead. Feel free to share your screen and take it away.
Okay, good morning, everyone. I'm Shawn Veurink with RPM Solutions, and co-presenting with me today will be Claude Strope from OPPD, like Jerry introduced. First slide we have is we're going to talk today about is consumable and nozzles. And go to the first slide. So on consumable nozzles today, we'll talk about design and quantities on typical atomizer wheels and discs. Nozzles can range from a few $100s a piece to, so a set will range from a few $1,000s to several thousands of dollars, depending on quantity and material. We'll share the common carbide materials that the nozzles are made out of, and we'll compare the costs, the hardness, and the estimated wear life. The life of these carbides have improved over the years, and the attention now is coming somewhat toward the cup features. So we'll go over some cup features, and lastly, we'll go over some reverse taper nozzles that we use at some customer sites, including Claude's site at OPPD. So the first thing is design and quantities, just to kind of give a generic overview of what the nozzles look like in the atomizer wheels and discs and some of the quantities. So you can see the inlet and the outlet and the quantity of the different type of nozzles range from anywhere from quantity of 8 to 32 in a few of these wheels. The first nozzle on the left would be in like an anhydro wheel. The next one would be more toward the ABB flacked wheel. Then we have some of the Nairo and Alstom or GE nozzles in the other instances in this example. So anywhere from 8 to 32, depending on the wheel and the wheel size and diameter. And most of these are locked in with an O-ring and a step, but some of them, as you can see on the left side, are locked in with a taper. Some of the wear material comparisons for these nozzles include tungsten carbide, aluminum oxide, silicon carbide, and boron carbide. There are others, but from my experience, these are the most common. Tungsten carbide is sometimes used, or mostly commonly used in stationary applications, but is not routinely used in rotary components because of the high density and the unwanted stresses that it might cause. Aluminum oxide is used in some nozzle and some lower wear ring applications, but again, in the more abrasive instances, it doesn't perform as well. So the next two materials, silicon carbide and boron carbide, are the most common materials that perform well in aggressive applications. Silicon carbide and boron carbide are very comparable in price and performance, and it all depends on quality of the raw material and the sintering process. To the right, I'll show a difference between good quality carbide versus poor quality carbide. Just a picture of a couple nozzles that ran in the same atomizer wheel for the same amount of time, and one had quite a bit higher density than the other. So the performance is very is better on the one on the top. Let's see here. So, and I'm going to throw in a fifth material to kind of give a comparison, which is referred to as a diamond carbide, on the very right of the chart. Let's see here. Whoops, sorry. Trying to move my text here. So our company started using the diamond carbide back in 2011, and to date, none of these nozzles have worn out, and I predict that I might never see one of these nozzles wear out. They perform very well. The only negative of these nozzles is the cost, and it's typically 25 to 35 times the cost of silicon or boron carbide, and you can see that in the chart. Later in the presentation, we'll discuss how we're able to utilize this outstanding material in nozzles. So cup features. From first glance, sometimes you might look at a nozzle and it seems completely wore out, but the reality is that the carbide is in great shape and the cup is either corroded or eroded away. In most instances, the cup can be replaced for a fraction of the cost of a new nozzle. So we've done a few things with cups over the years. First thing is hardened rings. It's to help prevent the wear on the inside of the wheel. This usually happens with users that have nozzle blanks. It seems like it happens at the nozzle that's right after the nozzle blank. It creates a lot of turbulence right there and creates some wearing on the cup. So just to give you an idea what a new nozzle looks like with a hardened ring, and it's just a material that's on the inside that has a higher wear rate. There's a nozzle that's run or that has an upper or a hardened ring and is run for several thousand hours, and then on the very right is a nozzle without a hardened ring that's run the same amount of time. So that's an improvement that's been made to the cup to prevent it from premature discarding. The rotating or rotation pinning. This is a feature that has been implemented to provide the end user or provide the end user a precisely way to rotate the nozzle. The number of slots used by end users are typically anywhere from 4 to 6 and sometimes even 8 slots. So I'll move over. So what it is just has a slot with a number so that the nozzles can be rotated equally each time and be right in the right position for every rotation. And then lastly, on the cups, we've done some material upgrades. In high corrosion applications, titanium and Hastelloy are standard, but in most applications, the material is stainless steel for the cup. And to prevent premature discarding of the nozzle, of the corroding of the stainless steel, the cup can easily be upgraded to titanium for superior corrosion resistance. So now I'm going to turn it over to Claude. Claude's from, like Jerry introduced him earlier, is from OPPD, Nebraska City, lead systems engineer. So take it away, Claude.
All right. I guess first make sure you guys are hearing me.
Yeah, we got you, Claude. Thank you.
All right, great. So I'm with Omaha Public Power District, as already mentioned. I started off as an operations engineer for about 12 years, working in a two-unit system here. And recently I've moved over into the systems group, which is kind of a new technique for us as a plant. But so we had a new unit. Unit number 2 was constructed and went operational in 2009. As mentioned here, 740 megawatts. It's one of the last plants that was constructed here in the United States. And as such, it's got all of the best achievable control technologies. I consider it one of the cleanest plants in the nation. Unit 1 is much older, uses a precipitator. So as most of you know, they usually go off of a site emissions when they look at plants and stuff. And because of that unit, we never get put on any of the top plants. So that's where we're at with Unit 2. Original scrubber constructed by Alstom. And we are in, it was a lime only system to start with. We ended up using a lot more lime than was predicted. And so this last year, we've been in the process of installing an ash recycle system and trying to commission that. So let's go on to the next slide. So many years ago, I think it was around 2013 or so, we got together with RPM Solutions and started trying their reverse taper nozzle. And as many of you with awesome systems are familiar with, we've got 2 SDA vessels with 3 atomizers in each vessel, and it's not an easy thing to make a swap from one type of nozzle to the other, because you don't take all the atomizers all out at once typically. But we had an outage, so we were able to swap everything over all at once. And following that swap, I estimated that we had a reduced lime usage of varying between 2 and 7%. Very difficult to really quantify, because we couldn't go back to the old system, and ideally we would have switched back and forth a couple times. But we made the swap. We liked what we saw, and we've stayed with the reverse taper nozzles for our system here. Don't know where we're going to go with the recycle system. I really, at this point, don't have a reason to go back to the original style nozzles. So I'm not sure if we'll ever quantify what happens with an RTN nozzle. During that testing process, the reason why we were able to get drier or lime savings is because our fly ash was drier. We were able to drop our outlet temperature by a couple of degrees. And over time, I've determined that 1 degree drop in outlet temperature for us was equivalent to about 3% savings. And we haven't had enough runtime on our recycle system to really see the impact on the recycled fly ash at all. So what are some of the additional things that we have seen? And with the original design nozzle, where the taper it starts off larger on the inside and reduces down to a smaller hole on the outside, we would see plugging on those. Like if we had a chip, some debris or anything like that, it could enter into that nozzle and then get stuck in that larger or in that smaller section of the nozzle. And then we would also get buildup of lime slurry solids as it dries out. We would end up seeing plugged nozzles when we went to do maintenance on the atomizer. And with the reverse taper nozzle, we just haven't seen any of the nozzles being plugged. We also see a lot of increased wear on the nozzle life. I think Shawn points out later in a slide here, we have not changed our ceramics in the, 6-7 years we've been running the ceramics. And before, we could get maybe 1 or 2 maintenance cycles out of a ceramic nozzle before we had to replace the nozzle. I think a lot of that has to do with just the taper on the nozzle itself. Maybe Shawn's using a better material on these, but the reverse taper nozzle, as it tapers outward, you're going to get less force on the nozzle itself as that stream spreads out, and I think that has a lot to do with it. Just a lot less force and pressure on the wear surface. What we also saw, it was the insert ring of the wheel. I found a couple pictures, but I don't know if I can get them showing up here or not. But we would see. I don't want to try to mess with the system. So what we would see is coming off of the nozzle on the original style nozzle, it has a pretty large flat area on the nozzle outlet, and that is flat, whereas the ring has a circumference on it, and that flat spot on that nozzle would cause upset flow condition around the ring, and that would create pretty dramatic wear patterns on our ring. And if you're not careful on these rings, they will fly apart. There's a lot of stress involved with the speed that they're rotating, and you don't want to be you don't want to be a part of that type of a situation with a ring flying apart. But the original nozzles would create very sharp edged wear patterns, and would cause us to have to decommission that ring fairly quickly. With the reverse taper nozzle, there's a lot less surface area on the outside, and so we've seen a completely different pattern of wear. The wear pattern is very smooth, and I think I probably get 4 or 5 years out of a ring, where before we were having to replace them maybe year and a half time frame. So it has helped on that ring wear also. And what we also are seeing on the SDA vessel, we've got discharge on the bottom of the vessel itself. As you get unbalanced flow, you'll get some wetting of the walls that dries, it builds up, and over time it gets to the point where it can't hold itself up, and it'll fall off the side of the wall and drop into the bottom of the SDA cone. And with the reverse taper nozzle on lime only, we have seen quite a bit less plugging, which would indicate to me that we get less wetting on that wall. The fan pattern gets better contact with the flue gas as it flows through the stream and dries faster. That accounts for our drier fly ash, and we've had a lot less plugging as a result of that. Okay, you can go to the next slide.
Hey, Claude, real quick question for you.
Yes.
Maybe you're going to answer it here. If you do, let me know. And in terms of, you mentioned less like wetting and everything in terms of switching nozzles and having a lower outlet temperature. Is that more a function of the spray pattern or the particle size, or just overall the reliability that you're seeing with these nozzles, or a function of all those? What would you kind of attribute to at this point?
Well, part of it would be a function of all of it, but as this slide shows you on the spray pattern, very significant difference on how fast it spreads apart. And so, the name of the game in these spray dryers is surface area. The more surface area you can get, the more aerosol particles you can get, the more surface area you get, the faster it dries. And so I really attribute it to the fan pattern on that bottom nozzle, and not having the momentum to get to the outer wall because it gets dried faster. And Shawn, do you want to go ahead and take over on this one, or?
Absolutely. So as Claude was saying, we've got a standard nozzle on the top picture and the standard nozzle spray pattern that's simulated. Of course, the picture on the left of the nozzle is an actual nozzle. It's not one of Claude's nozzles, but or an Alstom nozzle, but it's a Nyro nozzle. Kind of give you an idea what the width of the spray pattern is with a standard nozzle, and then on the lower section is a picture of the same size nozzle that's been replaced with a reverse taper nozzle, and you can see by the wear of the cup actually, and where the lime slurry, the dried lime slurry is not in the nozzle, how wide that spray pattern is when it's operating. So, and you can see on the right hand side, the reverse taper spray pattern, kind of a simulated what it would look like. So of course, larger spray area, the wear is significantly reduced. The nozzle profile is maintained longer, and consistent spray pattern. So next slide would be, so how do we handle these nozzles? Because we're implementing some of the diamond carbide material, of course, the high expense. And then, so how we're doing that is through a lease program with our customers. And actually, these are pictures from nozzles that Claude sent back to me, but it's a routine thing for Claude to send a set of nozzles back for actually recupped. And this one here came in this week. This RTN, the upper left-hand corner picture is a nozzle that was supplied back in April 2013, and then and then the picture to the right is just a shot mostly of the carbide, but you can see the cup is pretty wore out, and but the carbide is not. So we removed the carbide, put a new cup on it, as you can see down in the lower left, and then the lower right, and we'll return that set back to Claude or the customer probably by the end of this week. So just a few days to turn them around and get them back to Claude, and he can rotate them. And you can also see the pinning feature. Claude has four slots on his nozzles, and they're numbered 1, 2, 3, 4. So he pretty much rotates them, if that's correct, Claude, one time around in all 4 positions, and then sends them back for recupping. Is that correct?
Yes, that's correct.
Okay. So, and that's all we have. So if you have any questions, please ask now, and or contact the Dry Scrubber Users Association board, or through the website, or you can contact me at RPM Solutions and Claude at OPPD. So thank you.
Thank you, guys. Appreciate it. Yeah, I did have a couple questions, so I'll fire away here. Claude, I know you mentioned the recycle ash implementation, and you talked about lime consumption being higher. Was the implementation of the recycle ash a function of the fact that lime consumption was higher, or what was kind of the driver for implementing the recycle ash system?
Yeah, so it was 100% for lime consumption. For those of you who saw Primex's spreadsheet last presentation, you can go back into the old presentations, pull it up. He had shown a chart of lime consumption of many plants throughout the nation, and the left was on the low end and the right was to the high end, and we were pretty much all the way to the end of to the right side. And so it's primarily lime usage.
Gotcha. Do you guys have an expectation on what kind of percentage lime consumption you'd expect to see by implementing the recycle ash?
So we sold the system to upper management based upon a 20% lime savings, and I'm not going to get into what we're actually seeing because we're still in the project phase of it, but we are seeing more than that. And so hopefully maybe later in the summer, I can share more of what we're seeing.
Yeah, that'd be great. It's interesting to hear that. So, good. Well, that's excellent news. We did get a question on the Slido for you guys. What is the optimum recycle ash moisture?
I'm not able to answer that because I don't have enough experience.
All right. Um, have you guys, I guess in some spray dryers, I've seen this because I know typically, for example, the spray dryer, a lot of moisture and slurry control is done at the same time. Have you guys had any struggles with that or seen any implementation of some sense of independent temperature control and slurry control?
So our system, I can just kind of go through a little bit on our system. And of course, this started off as a lime only, but we will continue utilizing it through the recycle ash. So with the Alstom system, we have three what we call finger ducts into each SDA vessel, one serving each atomizer. And because of the rotation of the air preheater, we get one duct that is about 30 to 40 degrees hotter than the third duct. And then the middle duct is about in the middle, but it's got 11 degree swing across the duct as a whole. So we get quite a bit of temperature swing across those ducts. And as a result of that, um, we do adjust the amount of slurry going in, and I say slurry as all a complete stream, water, ash slurry, lime, everything. It is adjusted according to temperature. And that allows us to try to get each atomizer to have the same amount of dryness of the ash coming out of that stream to maximize our outlet temperature reduction. We added approach temperature where we are controlling the difference between the dew point and the actual outlet temperature. And that we see probably a 10 to 15 degree swing in temperatures as your load goes up and down. And so that has resulted in a significant amount of lime savings with that, probably in the course of 30 to 40%. And then we have installed into each finger duct flow measurement devices, and have seen that we have more flow differential between the ducts than what the design calls for. And we implemented them, but found just too much inconsistency in the readings, and it's not the magnitude, but the operation of the probes that we're using just wasn't. You have to have all of them working for the system to work. And so I'm in the process of using those as a guidance, as a historical guidance of flow. And I'll be using a matrix. So when we have these two atomizers in and on one side and this one on another side, then the flow balance is 0.8, 0.6, however that works out. And so depending on the atomizers that you're running, each configuration has its own flow profile. And so we've been working on implementing that. And that'll be a static system based upon historical data from the probes. Does that answer the question on so, and then when we're using I'll go back, our original system was a direct injection to where we have lime slurry coming in on one valve and dilution cooling water coming in on another valve. And we proportioned those to try to get close to the same slurry solids going to the atomizer. So the one that was flowing the most combined flow would have a little bit more slurry based upon temperature, lime slurry based upon temperature, but it would also have the water adjusted to try to get that solids content to be common across all three atomizers. Our new recycle system is a head tank design, and so it automatically does that solids adjustment. And so we do temperature adjustment with that head system, tank system, and we will be using the flow as we progress down the road.
Okay. Now with the recycle ash, any considerations as far as the nozzle, any different nozzle design or modifications, or just anything that you guys have learned to be aware from a nozzle perspective with the recycle ash?
At this point, we're using the same nozzles. We've been in the process. We were using the ferrotic wear plate on the bottom of the wheel. We're kind of monitoring it at this point. We used to get probably 3 or 4 years wear on that ferrotic plate. And so we'll see how that is impacted by the recycle ash. I assume it's going to be higher. And so we'll reach out to like RPM, and they've got ceramic plates that are available. The upper the lid to the disc, we'll also see wear on that, and we have been switching that over to a modified design that RPM has provided to us that is a ceramic, so that we won't see any wear on the inner lips or on the top of that plate anymore.
Okay. All right. I see we're down to the last couple minutes. So Claude, thank you. Shawn, thank you guys for the presentation and answering the questions. If anyone else that's, watching this live or, watches the future recording, you got some questions, then send them on through, Dry Scrubber Users Association. You should be able to find the link in this presentation. So yeah, come visit us, send us the questions. We'll get in touch with any one of the presenters and follow up and try and get some responses for you if you come up with questions later. But from here, again, I want to say thanks to Andy and Maggie, as well as Shawn and Claude again, for taking the time to put together this work and give a presentation. We sincerely appreciate that. Also want to thank the DSUA sponsors one more time. And again, please do come, go to the DSUA website, go check it out, get to know our sponsors a little bit, and again, big thank you to the board members. They've obviously been instrumental in helping make this year happen, and obviously an evolving climate from what it has been historically. And especially Travis, you heard him chime in here behind the scenes. He's done a lot of heavy lifting on the production side, getting these webinars going. So, big thank you to everybody. So we'll close it out. Say, hope everyone has a safe and happy and Merry Christmas, Happy New Year. And we look forward to seeing you guys back in 2021. And if you guys need anything or have questions, reach out to the website. Come find us on LinkedIn, send some questions there as well. And until we hear from you otherwise, we'll catch up to you in 2021. Thank you, guys.